So I have to. Okay. So hello, and thanks a lot to the organizers for giving me the chance to share our ideas on rotational cooling. Also, we are looking at systems that are somewhat different on what most of you are interested in. So I'm working in the quantum dynamics and control group of Christiane Koch in Berlin. And this, let's see if the pointer works. Here, okay. What I am mainly interested in is the control of rotation of quantum rotation, and in particular the control of asymmetric top rotors. So why asymmetric tops? So here are two examples why they are interesting. One is a proposal to use the rotational states of asymmetric top rotors for quantum error correction. And the other example, and not the least one, is that chiral molecules are asymmetric top rotors. And by now we have heard two talks telling us why chiral molecules are interested. So if we want to control the rotational dynamic, so here is a sketch of a spectrum of an asymmetric top. And if we want to control the rather complex rotational dynamics in an asymmetric top, we need some means of cooling the rotational states, or at least to be able to deplete some thermal population from a subspace of rotational space that we are interested in. And since the systems or the molecules we are looking at are far too complex to attempt any sort of direct laser cooling, we rather look at molecular ion and at a setup where we co-trap a molecular ion with an atomic ion. Such experiments are done mainly with two atomic molecular ions, and the idea is that in a trap, the motion of the molecules and the motion of the atomic ions are coupled, and so one can cool the motion of the atom, or laser cool the atom, and then sympathetically, because of the coupling between molecule and atom, the motion of the molecule is also the center of mass motion of the molecule is also cooled sympathetically. And what we propose is to use this setup to also cool the rotational degrees of freedom. That is, to find a way to couple the rotational degrees of freedom of the molecule to the trap motion. So, and as being theorists, we can be bold and put something rather large in the trap. So this is the setup we are looking at. We have a rather large molecular ion, in this case a glutamine ion, co-trapped with two ytterbium atoms. And well, they perform a collective motion in this trap. We calculated the normal modes and found that for this center of mass mode, the motion of the atoms and the molecules are coupled. And I should not forget to put here this little polar molecule in the headline, because what is important that the molecule has a dipole moment. And actually, this glutamine ion is also a chiral molecule. That means it has the dipole moment has 3 perpendicular components. And the dipole moment can then couple, or there's a dipole interaction between the molecular dipole moment and the electric field of the trap. And this dipole interaction depends on the orientation of the dipole moment, that is, on the orientation of the molecule with respect to the electric field. And the molecule also sees different field strengths depending on where in the trap it oscillates. That is, this dipole interaction couples molecular rotation to the collective vibration of the particles in the trap. And one can show that this coupling gets particularly, or it's at least reasonably strong, if a rotational transition is resonant to one of those trap modes that couple the molecular and the atomic motion. So normal mode frequencies in a trap are of the order of a few megahertz. So can we find the rotational transitions of that order? And this is the nice thing of asymmetric top molecules, that they have such diverse level splittings in the rotational level, in the rotational spectrum. So there are a lot of gigahertz transitions, but there are also sets of closely lying rotational states that are spaced by several megahertz. And we could have calculated the corresponding dipole coupling, and it turns out that we see a splitting of the energy levels due to the resonant dipole coupling that is in the order of 10 kilohertz. So the question is whether this coupling between rotations and the collective vibration is sufficiently strong to attempt any sympathetic sideband cooling. So we did a simulation of the sideband cooling of the atomic ions in the presence of the dipole coupling. And what we see here is the population of the two coupled rotational states. This is the upper rotational state, and this is the lower rotational states. And you see the different blue curves because the rotational spectrum is degenerate. We have all those, this is a j equals 3 rotational state, so we have m levels from 0 to 3, and the coupling the coupling strength depends on m. And if we do some with sideband scattering on the ytterbium atoms, we see that almost all rotational levels decay from the upper to the lower rotational state in a few milliseconds, except the state m equals 0. And well, that's again rotational selection rules. There is this m equals 0 transition is simply dipole forbidden, so we do not see any decay here. So what do we have now? Here is again a sketch of the of a subspace of the rotational spectrum of an asymmetric top. And when we apply sideband cooling to the atoms, we now have a kind of decay channel between two rotational states, so that everything from this upper rotational state decays to the lower one, except for this m equals 0 state. So that's nice, but that's of course not sufficient cooling, because what we want to is to deplete an arbitrary rotational states, and not only this one that is by chance resonant to a trap mode, or even to cool the rotational distribution to a single rotational state. Now, and we propose to do that by combining this sympathetic sideband cooling with microwave excitation. So here's the idea. So again, we have these two rotational states that are coupled and form, let's say, our decay channel. And now if we want to deplete an additional arbitrary rotational level, we can first drive a cooling cycle and cool and deplete everything which is in this highest level here, and then coherently drive the transition from the level we want to deplete in addition to this state by a resonant microwave excitation, and then run an additional cooling cycle. And we can show that if we repeat this cooling microwave excitation, then we get from having all those, in this case, 3 rotational levels populated, we can empty here these levels which are in black lines, and get all population in a single rotational level. But of course, this is still not a single rotational state, but an incoherent mixture, a degenerate incoherent mixture of rotational states. So the question is, can we also cool such a rotational distribution to really a single rotational state? And we found a microwave. We've also found a microwave protocol to do this. This requires actually two color or two microwaves with two different frequencies. And we need a circularly polarized microwave field that drives on the same transition where we have the cooling, so that we can get all those drive all those degenerate states here to the single rotational state. So, and there is one point that I would like to mention on with respect to this. So what we have also tested is how sensitive these protocols are to the imperfections in the microwave polarization. And we found that depleting or cooling everything up to a degenerate rotational to a set of degenerate rotational state is fairly robust to imperfect polarization. But if we want to go from degenerate rotational states to a single rotational states, this really requires a very good or requires that we have good circular polarization. And I'm mentioning that because I was very happy to see to hear earlier this week about these improved microwave antennas with very small electricity that were used for this microwave shielding. Okay, and this with this I already come to the conclusions. So I showed you our ideas on a sympathetic cooling scheme for asymmetric top states that works in combination with microwave excitation for depleting either an arbitrary subset of rotational states or cooling to a single rotational state. And this is also by now on the archive. And what I would like to emphasize is this is all happen in the electronic and vibrational ground state, and thus does not depend on the electronic structure of the molecule, but just on rather depends on rather, let's say, more simple properties like mass, rotational constants, and particular the dipole moment, and is so easily one can easily apply to many different molecules. And well, what else as an outlook? Well, these were our first calculations on that. And there's certainly a lot of room for optimization and improvement. And I just want to, as a last thing, mention that we are also looking at the dipole-phonon coupling in diatomic molecules. The system we have in mind here is thorium fluoride ion, and here it will be hyperfine transitions that couple to the that drive the phonon the coupling, the dipole coupling between the phonons. So this is a collaboration with Ferdinand Schmidt-Kahler. And with this, I'm at the end of my talk, and thank you for your attention.
Thank you very much for this very nice talk. Time for questions.
Thank you for your talk. It was nice to see someone else work with a big molecule. Well, my question is maybe a bit how could actually atomic ions and molecular ions coupling to each other? What mediates the coupling?
The trap mode. So in this ion trap, the electric fields that form the trap plus the Coulomb repulsion between the ions leads to the, let's say, it gets the kind of harmonic potentials in which the particles form kind of normal mode vibrations.
Ah, okay.
And that's the collective vibration that couples the center of the mass motion
Ah,
in the
okay.
trap.
One short question maybe. How easy do you think to cool CHD bromine iodine?
For this, I mean, we are thinking in this direction, but for this we will certainly need to consider the hyperfine structure of the asymmetric top states, which is on our agenda, but will make things more difficult.
Okay, thank you.
Thank you. Very nice talk. My question is about the micromotion. Is it affecting the cooling?
The
Motion
micromotion,
of the ions.
with the micromotion, you mean the oscillations in the
Well,
trap?
beyond desire, yes, because they're trapped. You are having a pole trap, and
Yeah,
there is
yeah,
some
yeah, yeah, yeah.
residual heating.
So, I'm not sure if I'm understanding the question correctly. So the idea is that we must be in a condition where we can do resolved sideband cooling, so that we are reasonably cold already to do that.
Yes. So the time scale at which you do the cooling, and how long is compared to the macro motion.
With the macro motion, that's something I have to. What time scale would that be happen? Do you have? I would have to check that. So the time scale for the cooling is in the microwave millisecond region.
Okay.
So
maybe
we have to.
should-
We
we
have
should look.
definitely to check that.
Okay, I think we should stop there and thank Monika again. Thank you very much.